All right, so we've got a little bit of an we're actually projecting and another one up here with the presenter notes. So if it ever looks like we're on the wrong page, it's because we are on the wrong page. So we're here to talk about Google Dapper, the byline, a large-scale distributed systems tracing infrastructure. I want to start off first by saying thank you very much to Engine Yard for hosting. And I also wanted to say a very special thanks to Inez for setting up San Francisco. When I saw that New York was going to have one of these, I suddenly got very, very jealous of New York. And Inez has now tempered my jealousy of New York. So thank you, Inez. So a little bit about the two of us. My name is Ryan Kennedy. I run infrastructure engineering over at Yammer. I've been there for about 3.5 years, long enough to know the wonderful days in free Microsoft.
I'm Anjali. I'm the latest edition on Ryan's team.
So quick show of hands, who's actually read this paper? Yes! Oh man, this is like every college professor's dream that people actually came. So this paper was released in 2010 by Google. The one reason I want to call it out is it's 4 years, right? 4 years is kind of a long time in technology. And so remember that everything that's being presented here is being presented with about a 4-year lag. I was actually able to get in touch with some of the folks who are still working on Dapper right now, and it sounds like actually a decent number of things actually changed under the hood. So realize that we're looking at kind of a snapshot state of Dapper from when it was deployed a little while ago. This is not exactly a research paper. This is more of an experience paper. A lot of papers you pick up, you read them, and you think, wow, this is some research student, and this is part of their dissertation, and there's a bunch of math symbols in it, and oh my god, this thing is terrifying to read, and I have to read it 50 times to figure out what's going on. This isn't one of those papers. This is about sort of a practical life experience type paper. We had this problem at Google. We needed to solve this problem. We built and deployed this system, and we thought it was novel enough that we wanted to take it out to the world and tell you all about it. And so as a practitioner myself, I found this paper to be very approachable, especially because a lot of the problems that are described in the paper are the same kind of problems that I have to deal with and that I see day in and day out. And this is one of the reasons why I really wanted to present this paper, in that it's not sort of the typical paper that you read a lot of times. So Anjali, we'll talk a little bit about what is Dapper.
Thank you, Ryan. So before I say anything, I just want to thank Ryan for giving me a chance to co-present.
A little louder, please.
Oh, sorry.
Hard to hear you back here.
Oh, okay. So before I say anything else, I wanted to thank Ryan for giving me a chance to co-present. I've also never done one of these things before, so I'm probably going to screw something up, so appreciate it if you guys cut me some slack.
Sorry.
So anyway. Thank you, one person in the back. Okay, so anyway, so what is this thing called Dapper? According to the paper, Dapper is a large-scale distributed systems tracing infrastructure. What does that even mean? So let's look at what each of these terms actually mean. So according to the book Distributed System Concepts and Design, which was the most qualified definition we could find for distributed systems, the definition states that a distributed system is a software system in which components located on network computers interact by passing messages. So let's try that again more slowly. A distributed system is a software system in which components interact on network computers by passing messages. So what that really means is like you have a collection of services spanning a collection, spawned out across a collection of clusters, perhaps hardware clusters, and they interact by passing messages, presumably these days through HTTP. So what exactly is a tracing infrastructure? At a high level, this would actually mean it's software that interacts with a distributed system so that it logs the execution of flow through the system and records data as it makes its way through without actually interfering with the overall execution of the system. And large scale essentially means the capacity and size of the distributed system, the one that's actually being traced. So in a nutshell, that's actually Dapper, a large-scale distributed systems tracing infrastructure. So in Google's own words, like, why did they build this thing called Dapper? They built it to provide their engineers with more information about the behavior of complex distributed systems. So let's stop for a second and think about what this means, right? At Yammer, we have something like 30-something backend services by now. We started with 1, and then 2, and then, today we have a team of like 100+ engineers. And each team is responsible for different sections of service, different services, or different sets of services. So if you actually really stop to think about this, like a single product is manned by all these services in the background. And so comprehensive tooling for such a system to find out like where exactly the bottlenecks are, which cluster of subsystems is not behaving at any given point in time. This kind of tooling is like very hard. Most companies have their own internal tools to help with these kinds of scenarios. And without that kind of tooling, like debugging at production or like runtime, you're just making a series of educated guesses, and that can be very painful and unperformant, right? Once you throw organizational boundaries into the mix, like you have managers responsible for different teams that are responsible for different services, which is usually the case, that becomes even more complicated. So just think about it, like if on a Friday night, like Ryan calls me and he says, hey Anjali, I'm not at my house right now, but I'm trying to search something on my phone, and the search thing is not working, can you look into this? And I say, okay, so our team is responsible for search, and this service is B and C that it calls. And I look at B and I'm like, oh crap, this is taking a really long time to respond. But I don't know anything about B. I don't know anything about the internals of B and how it works, right? But what I do know is like there's a manager who's responsible for B. So what do? I call him, right? And the first thing he goes is, oh wait, we had a new endpoint for a service C that shipped this week. Maybe that's not behaving so well. So what does he do? He calls a tech lead for that service. So you can see how this starts to like fan out. Like, I'm responsible for one service, I call another person who calls another person. And it would be much better if you actually had software that actually did this for you, that told you in runtime that, you know what, there's this span out between your services, and there are these endpoints that are probably not responding very well. So what Dapper helps you to do, it's a very long-winded way of saying what Dapper really helps you to do is reap the benefits of a distributed system while offsetting some of the costs. And Ryan will do a much better job of explaining all this in the next few slides.
So distributed systems, let's talk a little bit about that, because a lot of what Google's trying to do, like Anjali said, is trying to offset a lot of the costs of distributed systems so that you can reap a lot of the benefits of them. So this kind of in a nutshell, it's taken straight out of the paper, this is kind of a small distributed system, right? In this case, what you're seeing here is the trace of data and execution going through a web stack, right? This is kind of your classic end-tier application. You've got a user out here and they're sending a request to this front-end web server. Front-end web server calls these middle-tier servers, and those middle-tier servers call this back-end server. And this is this is the world of the distributed system, right? The messages are going back and forth. You've got a request message that goes in, a response message which comes back out. And this illustrates kind of the point that Anjali was bringing up, that I may be an engineer here working on front end A, and I know that A talks to C, but I have no idea that C talks to E or C talks to D. So when A becomes slow because C becomes slow, I have a really hard time getting insight and figuring out that C is actually slow because D is slow. This is kind of one of the wonderful, painful worlds of distributed systems, right? So let's talk about the benefits of a distributed system, and these are some of the benefits that we sort of realize ourselves at Yammer. The benefits are largely organizational, right? As your software company gets to a certain size, it becomes sort of untenable to keep working on things like the giant monorail, right? Twitter had this problem, Yammer's had this problem, a number of other companies had this problem, where you start getting to a point where you've got so many engineers checking in code to a single code base that it becomes a very difficult problem. It becomes hard to scale, it becomes hard to manage. At some point you have to start breaking components apart so that you can actually reason about your organization as well as your technical architecture. And so a distributed system allows you to break your software down into distinct services, right? Each service has a purpose that it's built to perform. It doesn't have to be this big kitchen sink of everything that your application does. They can be developed by different teams, which means you can actually start hiring for different teams, right? Teams who have maybe functional expertise in search, teams who have functional expertise in machine learning and other things. You can begin starting to decompose the application, begin decomposing your organization a bit so that you can actually start scaling beyond some of these bottlenecks that you have. Across different platforms, different programming languages, which means that each of these autonomous teams, they're free to go ahead and build whatever platform and whatever languages they want to, right? If one team decides that, all these libraries we're using are really better for C++, or this other language is much better for machine learning, or this language over here has got all the tools for search, they're free to go ahead and do that. All they have to do is set up the contracts for the message passing between them. And so this allows the organization to flourish, allows the architecture to flourish. Now, unfortunately, the downsides of a distributed system are all these same things we just talked about, right? Everything that made a distributed system great is also the things that make it just hell, right? The fact that you now need to get an answer on a particular system that you're talking to, you need to go find the right person in the organization that you want to deal with. You want to talk to a piece of software, you have no idea what other pieces of software it's talking to, right? I had a joke with someone the other day that the distributed systems or service-oriented architectures are kind of like the money laundering of the software world, right? You put something into the system, it goes rattling around, it pops out the other side, and someone receives this request and they're like, I have no idea where the hell this request came from, right? It gets washed as it goes through the system. And so it becomes very difficult to sort of gain any insights as all these requests and all the data starts flowing around the system. And so from sort of an engineering context, you as an engineer are now faced with the fact that you're dealing with multiple services, you're dealing with multiple teams, you're dealing with facts that you have these silos that are impenetrable. You can't really see through them that well, especially as the organization gets larger and larger. For us, we've, in the last year and a half, we've been acquired by Microsoft. And it was one thing when we had to sort of cross these organizational boundaries inside of Yammer, which is still relatively small, we're all in the same building. In most cases, you see people on a day-to-day basis. You get swallowed into a company the size of Microsoft or in a company the size of Google. Now all of a sudden they're in different buildings, they're in different countries, they speak different languages, and you have a really difficult time figuring out how you talk to the people managing these other services. They're all managed by different teams, we said, and they have different continuous deployment of services, right? Not only do you not know who the people are that's working on this, but you don't know when they deploy new versions of software. You don't know when service B talks to service D, and then push a deploy, and now instead of talking to C, now it talks to D and E, right? You have very little insight that you have as dependencies. And from an on-call perspective, it gets even worse, right? You as an engineer, you're starting to get a page because the system is slow, right? The worst page of all. The system is slow. Why is the system slow? I have no idea, right? And about the best you can do is if you've got really good metrics, you can tell things like, well, all of our requests are coming in and we're making requests to the database and the database is slow. Well, why is the database slow? I don't know, I don't run the database. Talk to the people who run the database. Or you're talking to some other service, right? You're talking to the machine learning service and it's slow. Well, why is it slow? I don't know why it's slow. I don't know how it's built internally. I don't know if it talks to some other service. And so if you're the on-call engineer and you start getting these pages and you know that you send this request into this black box and behind it maybe 1,000 other black boxes, it becomes maddening for you to actually try and diagnose this problem and even to figure out who you should engage to help you diagnose what's going on. It becomes, related to this, becomes very difficult to figure out which service is even at fault. Is it the system that I call? Is it a system that they call? A system that they call? And beyond that, you don't even know why that service is at fault. Well, it's slow. Well, why is it slow? All sorts of things have become very difficult with distributed systems.
So, thank you, Ryan. So, given all of that, what is this thing called Dapper again? A large-scale distributed systems tracing infrastructure. I just like the word so much, I figured I had to put it in this slide. So what is the problem space that Dapper attempts to solve? Like everything that Ryan explained, and then some. Typically, your end user will be an on-call engineer, right? She will have like a bird's eye view into the overall health of the system at any given point in time. And if I had to visualize how this worked, what I would want is to see a cluster of how the system is doing, possibly like a heat map or something, and if a particular cluster of subsystems or a set of services doesn't behave well, then that part of the graph heats up and you can zoom into that, ideally pull up that cluster or pull up a service within that cluster and find out which exactly is the service holding up the train, right? But at least in this way you have a much quicker procedure for drilling down into which service in your conglomeration of services is responsible for causing the problem anywhere in your system. Otherwise, what you end up doing is, like I said before, you end up just calling a bunch of people, making some random guesses or educated guesses, and manually checking things off the list, which is kind of unperformant the more and more services you start to have. There's also the benefit of long-term pattern recognition. If you can figure out a way how to store all that data in any given place and then search it, you can eventually start to see patterns like, okay, so I introduced this new service X, and this service X is actually now hitting this service Y. How has Y been doing over the last week or so with all these hits from service X? So that gives you a better understanding of the behavior of your system. What are the design goals given a problem statement like this? The most important thing that the authors found was ubiquity. Ubiquity means that it's pervasive. It's deployed everywhere. When you have an instrumenting agent, or your tracing agent, like it should be deployed in all the services of your system. So let's stop for a second and think about what that really means, right? So hypothetically, take a very simple case where you have like 10 services. You can't do something like saying, okay, I want to deploy this tracing agent only to 8 services, and these other 2 services are there, but they don't receive that many calls, so I'm not so worried about them, so I'll get only the data from 8 and that'll be okay. So if you can still do that, but you're not getting all the data from your system, you're only getting the data for 8/10 of your system. So what that means is eventually that will lead to things like false positives or just inaccurate data, because you're actually missing data from the 2 services that you actually left out. So ubiquity becomes the most important goal. If you want to get a picture of the overall health of your system, you want to do it for all services. Either you do it for all or you don't do it at all. So that's why it's so important. Like if you deploy something like this, you want to trace the health of your entire ecosystem. And then there's low overhead. For a company like Google, and if you think about a service like Google Search, low overhead becomes the next most important goal, or rightly the most important goal, right up there with ubiquity. Essentially what it means is applying a tracing agent to your application should have a very negligible impact on your request response latency. Meaning that it takes an almost negligible amount of time, or really doesn't impact like your response times. Application level transparency. This is something that when they mentioned in the paper, I'm really mucking this up now. Basically, developers should not have to be aware that the tracer agent is actually running. Tracing infrastructure that is actually tightly coupled to the application logic inherently becomes more fragile and less extensible. So let's stop for a second and think about what that means. If you have somewhere in your application saying the request is starting now, and so I'm going to start a trace now, and then it goes somewhere else and it creates some spans, and then it attaches some information, and all of that goes downstream, that may be fine for that application. But if you have to remove that logic and extend it to another service, now you're getting into a whole bunch of problems, because that logic is tightly coupled with the application logic and the design of that application. So this actually, if you muck around with the application logic, inherently your tracing instrumentation becomes less ubiquitous. So what you want is a tracing agent that you can apply around the application, but that the application is not even aware of. So in other words, when you're actually writing your code, let's say if you're doing a Rails app, okay, so you do whatever logic you have, it goes to the database. As an engineer doing bug fixes or feature development, you're not even aware that the instrument agent is running. Like it just runs in the background, and it sends off some bits somewhere. So you, as an engineer doing application logic, you shouldn't have to worry about that kind of stuff. And the way they achieved that at Google was partly because they were blessed with a certain degree of homogeneity. They talk about this in the paper actually, where they use primarily 2 languages, Java for front-end development and C++ for back-end development. And so what that did is that limited the number of frameworks they were able to use. And because they limited the number of frameworks, they were able to successfully instrument those frameworks, and that left them completely separate from the application logic. And by instrumenting the frameworks, the application actually used the frameworks, and then that enabled for just more ubiquitous deployment of the tracing agent. I'm not sure how well I articulated that, but hopefully some of it made sense. And scalability. So this is the last one, but this is a requirement or a goal unto itself. What this means is, like, as the number of requests on your service actually start to grow or increase monotonically, like, you don't want there to be a negative impact in the latency of that service. When you apply an instrumentation agent, as the number of requests grows, like, the latency should stay the same. Or if it goes down or up, that should be a function of the service and its logic itself, and not of the application of your instrumentation agents. There should be no effect. So let's talk a little bit about low overhead. Like, we all know what Google Search is, and I can't even imagine, maybe Ben here knows what the request hit rate is for some of the search services. But I can't even imagine what it must be like. I mean, some of our backend services at Yammer get like more than 1 billion hits a day. So if you do the math on that, it boils down to like 12K requests a second, which is quite a lot. So how exactly did Google achieve this kind of instrumentation? Like, what did they do to achieve the low overhead part, right? The first thing they did was they decided to sample a certain number of requests. And by choosing a really low sampling coefficient, like 1 out of every 10,000 requests, they eventually came to that number and decided that this is good enough for high throughput systems. And if you really stop to think about it, like in a high throughput system that services like thousands of requests a second, if there is like a particular behavior like that service has, chances are because it executes so many times, even if you sample a very, very small percentage of requests, you're going to catch that behavior at least once. And also don't think about this in the context of like a single server. Remember that you all work at companies, but depending on the scale you're at, like you may have tens of servers or even hundreds of them. So if you apply the sampling coefficient across all of your servers, you're getting data from all the services across all of those servers, which is quite a lot of data. So it actually shouldn't be too high, in fact, because then you'll be collecting too much data, and that will end up being white noise. So you want like a good enough portion, and that depends on every company what you want to set it to, but the idea is not to set it very high if you have a high throughput system. They also did something called adaptive sampling, and that was published in the paper, but it was being deployed at the time, so I don't know what the end result was. But what it really boils down to is that they started to realize that just because a certain set of services have a very high throughput, so if you think like services in the search cluster have a super high throughput, they have all these like performance requirements. But there are services in possibly another ecosystem that, they're not slow, but they don't have the same throughput requirements. So in that case, setting a sampling coefficient to be so small, you're actually missing good data because you're not servicing enough requests. You want to instrument more requests. So how to do this without getting application engineers to go in and muck around with like the configuration parameters and say, okay, now I need to change the so many requests out of so many requests need to be sampled, and that's a no-no. So what they did was they tried this thing out called adaptive sampling, which applies some kind of probabilistic analysis based on the throughput of your service or the expected throughput of your service, and automatically adjusts the sampling rate. So that's pretty neat. And that might be worth considering if you have different services that have different throughputs in your ecosystem. They also did something called out-of-band data collection. So I think it goes without saying that trace data should be collected outside of the request-response cycle. But there are multiple reasons why something like this needs to be done. If you stop and think about it, right, every client sends the server a request. The server sends a response back. Like, you don't want to wait until the entire fan-out of services has happened to send all that data back, right? So let's stop for a second and think about it. So the client sends some information over, and that's part of a trace. And the server says, okay, I got this information, but now I'm calling services B and C call some other services. So for each of these services, you're sending that trace data along, and if you wait until it comes back, and in the case of like a large set of services, you can have like enormous volumes of trace data going back, whereas your actual response headers may be only tens of kilobytes in size. So what you do is you end up chewing up network bandwidth for no good reason. And there's another reason you want to do this out of band is because many times in services we have middlewares that actually send the response back right away, and then they go on and make their calls or do some background tasks or something, right? So you always send a 200 OK response, and then you're like, task gets done, and then you want to send like some tracing information back to the client. Now you're actually interfering with the application execution cycle, and that's a no-no. So these were some of the constraints around which they actually had to build their tracing agent. So I talked a little bit about trace and spans and all that, so let's clarify that. So what exactly is this thing called a trace? In Dapper speak, a trace is a tree of spans. I think it's best conceptually modeled that way. And I'll show you a diagram in a bit. So think of it as one span for every RPC. RPC, for anyone here who doesn't know, sorry, not trying to be condescending or anything, RPC is remote procedure call, but the Dapper paper is littered with RPC everywhere. Don't literally take it as RPC. I think it's better to think of it conceptually as a service-to-service interaction, or calling a particular service's endpoint. Like it could be REST, It could be a call from your application to the database or the memcache, or for any one of these instances, like you could actually form a new span. So every trace has multiple spans. There's always one root span, and a root span spawns new spans whenever you make a new call. And within every span, you can have annotations. Annotations is application-specific data that you want to send along with your trace. So visually, this is what it looks like. So you remember that diagram Ryan showed you a little while before, where you have this front-end service, and that calls service B and C, and then C calls D and E. So this is actually the span tree that's modeled right along the lines of that little first diagram you saw there. So all these swim lanes is actually how long your request actually takes. And think of this as an entire trace, right? So the topmost block becomes actually your parent span or the root span. You can see how it has no parent span ID, so therefore it's the root span, it's the originating span. And then for every backend call it makes, it actually spawns off a new span. So you can see how the nested spans actually have a parent span ID. That is the ID of the span that spawned it. And so hopefully this makes sense when I say think of a trace as conceptually a tree of spans. And then every span can have its own list of annotations. One thing to note is that when you write something that instruments this, it's good to, at least for the basic level, like a good tracer agent should maybe log the start and end times of every span, along with maybe by default, like it should log like the service name that's getting called, like as the span name. The span name can be any human readable name. I'll show you an example of that in a second. So let's get into annotations for a bit. So like I said, annotation is any application-specific data you want to pass along with your span. And a span can have 0 to many annotations. And each annotation gets a timestamp and either a textual value, or it can be like a simple string like I'm the client span, and I'm sending a call to this particular server, so I'm going to tag myself with a new annotation called client sent. And when I get the response back from that server, I'm going to tag myself again with a new annotation called client received. So think about it, like, so now I have a span with 2 annotations, client sent and client received. Both have logged times at which they were logged, so you can actually tell how long your client side call took. And there's a similar way of doing things on the server side. So you can have a simple textual value, or you can have an annotations full of key value pairs. A little bit about instrumentation. So how exactly did they do all this? So if you think about this, like generating your trace, and then you have a span, a root span that gets generated when your request starts, and then as you go through your application, and for every endpoint you call, like you spawn off a new span, and then that gets tagged with some kind of default annotation. It seems all kinds of complicated, right? It shouldn't happen as part of your application, right? So they did this in Google by instrumenting commonly used libraries and frameworks. Again, like because they were blessed with homogeneity, having a pre-instrumented library was incredibly helpful to application developers, so they didn't have to worry about instrumentation bits. If you stop to think about this for a second, if you're a company that has a proliferation of languages executing across different platforms, each of those languages possibly uses different frameworks, this problem starts to get exponentially hard, because now you have to write an instrument agent across multiple frameworks, or frameworks that you think could be used, executing possibly across multiple platforms, which means different versions of the kernel, which means, and then you have to make sure that they work for every framework that's in use, and every time a new version of that framework gets released, you possibly have to change your instrumentation. So it just becomes a really, really hard organizational problem to solve. So homogeneity helps. And this is an example of a trace, of a sample trace in JSON format. So you can see at the top, like there's a trace ID, and a trace is a list of spans, and there's only one span in this example, but I think that's good enough. And then you have a span ID, and clearly the parent span ID is empty. That means it's the root span. It has a human readable name, something, a start time and a duration, and a list of annotations. In this example, the annotation is obviously emphasized, but there's only one annotation. And you can see how the name of the annotation is path to SQL. And so obviously it's a key value pair, and the value itself is a JSON block. So the sequel is insert into messages something, and then there's a start node and some other information like a path. So looking at this annotation, presumably it's the code path that you have to plow through in order to execute that SQL statement against the database. So this is not part of the paper. This is something we're working on at Yammer, and there's a Ruby agent for a Rails app that we use that we're implementing. It's in development. I'm happy to talk some more about this after the talk if anyone's interested. It's also not production ready yet, so caveat. So on to Ryan.
So Anjali was talking a lot about the instrumentation and the structure of all this data that you're actually trying to collect. And it's great that you can get your software to actually emit and collect a bunch of this data, but you actually need to coalesce all that data. You need to bring it somewhere where you can actually make use out of it, right? You've got a data center full of 10,000 machines. It doesn't help if that data just sits out on those 10,000 machines. You need to actually bring it somewhere for doing your analysis. And so you want to talk about how do you do things like, how do you effectively coalesce all this data? How do you provide data for immediate access, right? I want to be able, I'll call engineer right now. I want to be able to look at some of this data right now. I want to see what's happening at this very moment. In addition, I want long-term for pattern recognition, or I want to be able to do some sort of aggregate analysis on a lot of this data so that I can be able to say, it's interesting that I can look at individual traces, but I want to be able to look at lots of traces layered on top of one another to gain insights. And so you need a system that can actually deal with all of this. And this is another diagram out of the Dapper paper that it basically explains exactly how it is that they generate this information and collect it. And so what you have up at number one up here is you have a bunch of instrumented binaries. And so you've got your search application, you got your machine learning this, you got your web service that, you got your web front end here. They're all instrumented and they're all logging out to these files, right? Files on these individual machines. And then there's this Dapper agent, or Dapper daemon as they call it here. It's this little low profile daemon running on the box, picking up the logs and periodically shipping them off. And where does it ship them off to? It ships them off to these Dapper collectors. And it's the job of the Dapper collectors to then go ahead and take all this data and stick it into this central BigTable repository. And the way the data is actually stored internally in the system is using BigTable rows, one row per trace, keyed off of the trace ID. So if you happen to know a particular request that you want to go and look at, you can just go and index it by that. And then there's one column for each of the spans that's created. And this is one of the nice things that comes out of being able to use BigTable for this, is that you have sort of free-form columns you can create here, so that you can say that this was span 12 and it's for this trace, and span 23 went to this trace, and some of these others. Like this is sort of the sparse layout nature of BigTable sort of coming into play. One really nice thing about this is that Google was actually able to measure end-to-end latency on this stuff and figure out like how long does it actually take from the time that something is logged in the binary to the point that it's actually available down here. And the median time for that is under 15 seconds, which is more than adequate for doing a lot of sort of your on-call firefighting. Like 15 seconds of data behind, that's not actually that bad for being able to do on-call type stuff. I mentioned BigTable. Google implemented Dapper on top of BigTable. As I said, each trace is stored as an individual row. Each span is stored as a column. One of the things that we found out through talking to some of the current some of the Dapper engineers is that Google's actually expiring the data after a week, which means that they have a week's worth of data that they can go back and look at. So it's not like you only have the last 24 hours worth of data to look at. You can actually go back and say, this thing's blowing up today. What did it look like 3 days ago? Which is pretty impressive, in spite of sort of the amount of data that I'm sure that Google must just be chucking at this thing. So Anjali talked a bit about doing sampling at sort of the tracing level. One of the things that the Dapper paper brings up is that sampling is actually sort of a two-tier affair within Dapper. You have sampling that's going on at the application level in terms of exactly what's the sample frequency that you want coming out of this thing. In addition, the collector is actually doing its own sampling downstream from that. And what the collector is actually trying to do is the collector is trying to figure out, I'm writing all this stuff to BigTable, but BigTable is not it's not infinite capacity, right? It has finite capacity. I don't want to be the one that brings down BigTable for the rest of its consumers. And so they do a second tier of sampling so that they can make sure that they're metering their access to BigTable. The paper indicated the prod clusters were generating about 1 terabyte of data per day. And one of the interesting things that came out of the paper in relation to some of the discussions I was having with the engineers is that the Dapper paper talked about engineers wanting to be able to look back through like 2 weeks of data, but we found out they're only actually collecting 1 week of data. So we're not sure if this is a case where at one point they were collecting 2 weeks of data and they decided to truncate it down either because 2 weeks was too much and they could only really hold on to a week. Maybe it's the case that the traffic was increasing so much they had to crush it down. Or it's potential that users are users and they may have said, I want 2 weeks, but they went and looked at the analysis on it and said, yeah, but you're only looking at the last week. So, APIs, because everybody loves APIs, right? The primary way of actually getting data out of these things is this thing called the Dapper Depot API, or the DAPI. And the Depot API has a few different ways of actually getting the data out of the system. The first one is by trace ID. So we talked about the fact that BigTable is organized around one trace per row, which means the system's really sort of ideally set up to be able to just say, I have this trace I know about, I want you to go get this trace, bring me this trace. It's unfortunately not very interesting because it sort of requires that you know exactly that one request out of 50,000 requests per second that are coming in or whatever, that was the one request that you want and that you pray that was actually sampled. So it adds a lot of extra flavor on top of it for being able to do bulk access. The fact that it's built on BigTable means that it has MapReduce built in. And so you can do very interesting things, like you can say traces from the last 48 hours from these particular servers, and I want you to run them through this custom script that I've given you. And my custom script will take in a trace and decide what it wants to do with that, so that you can now begin doing some more aggregate information on top of it, which is where, for me personally, this is where Dapper gets much more interesting, is when you can look at data in the aggregate. And lastly, indexed access. So the BigTable is set up so that you can index into it by trace ID. The Dapper paper talks about a secondary index that's been built for this, which is a composite index built by the service name, the host name, and the timestamp for when a trace was logged. And what this allows engineers to do is, in a lot of firefighting, what you want to do is you want to be able to look at a particular host. And so this allows them to build an index that says, please seek to this service, this host at this time, and scan down for the next hour's worth of data and pull me out all the traces for this. So they've got a very optimized index for doing that, so you don't actually have to do a MapReduce for this. In terms of what the API actually gets used for, online web applications, the Dapper team actually built a dashboard for sort of the most common use cases that they saw the engineers would want. So the ability to actually go in and look at a trace or look at a selection of traces. But fortunately, or maybe just by chance, the Dapper team sort of understood that they weren't actually going to fulfill all the needs and all the wants of all their customers, right? They were either going to have situations where a customer was going to have a very specific request that wasn't really going to be worth their time to build, but that was going to be worth it for these developers to build. Or they were just going to have things that everyone's going to want that they never actually envisioned people wanting. And so having the ability to have this API for people to go and sort of self-service and build all these things meant that they got a lot of command line tools that were being built by developers, so that developers could go and say, I want a nightly report to go and run on this thing and give me the failure rate of all the things that are inbound into our mem cache. And for the things that are failing, I want a histogram of the source server that was sending them. And one-off analytical tools. So you're sitting in a meeting and a product manager asks you to answer a question and you have no idea, but the data's off in Dapper. Being able to build that one-off analytical tool really quickly to go and answer some of these questions is tremendously helpful and powerful. And so I mentioned the web interface. This is the one straight out of the Dapper paper. And what you can see here is sort of it looks not unlike if you use a profiler to profile your code, right? With some small differences, right? So you have in the first box up here, you have the ability to specify things like, I want to select all the data that occurred between this date and this date. And I want to scope it to this particular cluster and this particular user and potentially this job right here. So being able to really scope the data down. There's which node information do you actually want to pick out of that. Like in this case, they're picking out the RPC or the span name. So I want to know things like, this was the spell check RPC that got called here. And then also being able to indicate the cost metric that you want things to be bubbled up on. So in this case, it's selected on latency. They want to know how fast a thing is. But they also have cost metrics for things like the request size, the response size, the recursive size. So the ability to figure out how much data was shifted around if I do a recursive pass through the trace. And once you sort of give it the search, it goes off and running and it finds a bunch of traces for you. And so the top row, you kind of get aggregates. These are all the traces that we found aggregated up. And these two, E and R, are individual traces. And you can see that there's a bunch of calls here, there's a bunch of the total time spent, and you get some histograms for the time spent in them. And then this is the thing that initially drew me to Dapper, was the ability for Dapper to infer dependency diagrams in your architecture. One of the things I'm constantly asked for at Yammer is, Ryan, can you please draw a Yammer on a board for me? Can you show me all the systems and services. And maybe 12 to 18 months after I started at Yammer, I could still do this pretty well from memory. And then it started degrading pretty quickly after that as we hired more engineers and built more services. And people started saying, well, what about service B? And I'm like, what the hell is service B? When did we get service B? It basically got to the point where I couldn't actually hold that whole thing in my head. And so a system like Dapper is very appealing to me because Dapper just knows, right? Dapper knows that the search system called the getDocs system and the getDocs system called the thing2 system. And so Dapper can sort of sit there and say, I'm going to take this trace and this trace and this trace, and as I keep layering all these dependency diagrams on top, what you're going to get is one big overall map for what the system looks like. And so this is my favorite part of this talk. I don't actually care about performance. All I want is to not have people give me that disapproving look when I tell them, no, I can't actually draw that for you anymore.
Automated system diagram too, that's good.
Yes. And then you get this beautiful thing right here, right? This is the execution trace, and you can see where the time is going, and you can see things like green is actual time spent in the system, I believe, and blue is network time, and you can see things like, okay, this is the top level request, and it came in and it spent, 44-ish milliseconds, and I called this thing, and wow, what's this thing right here? It took from 7 milliseconds out to 20 milliseconds. It's like 13 milliseconds of time, but fortunately,